I'm super excited to introduce Jonathan Gair today for this July edition of the A3D3 Seminar. John did his undergrad at Cambridge, did his PhD at Cambridge, was a postdoc at Caltech, and then was back at Cambridge for a little bit, where most importantly, he was my master's thesis advisor. Then he was on to Edinburgh as a prof, and then now he's a group lead at AEI. And so his group does a lot of stuff, all things gravitational waves, but in particular, his group's really been driving forward using machine learning to do parameter estimation for gravitational waves. And so we're really excited within A3D3 to see what they've been doing and hopefully use what they've been doing in the next observing run. So anyways, big thanks to John for being here, and otherwise, take it away.
Okay, thanks. So feel free to ask questions as we're going through, or you can ask them at the end. I won't be able to see hands, so Michael, maybe you can monitor that, but people should be free to just interrupt if you want to ask something as we go along. So as Michael said, one of the things we've been working on at AEI in the past few years is building machine learning-based methods to generate posterior distributions on parameters of gravitational wave sources rapidly and robustly. This is work involving a number of people who are listed on this first slide, but in particular, Stephen Green, who's a postdoc at the AEI, and then Max Dax and Jonas Wildberger, who are both students at the Max Planck Institute for Intelligent Systems in Tübingen. So quite a few of the results I'll be talking about today have been produced by them. Okay, so I'm going to start by briefly summarizing current and future gravitational wave detectors. It's probably familiar to some people on this call, maybe not everybody, so I'll begin there. I'll then say a little bit about gravitational wave parameter estimation, so how we infer the properties of the sources that we're observing with current detectors. And then I'll describe various approaches to fast and accurate parameter estimation that are being used within this context of gravitational wave parameter estimation. These include methods called reduced order methods, but I will spend most of the time talking about neural posterior estimation, which is this work we've been doing in the last couple of years that aims to directly reproduce posterior distributions using machine learning techniques. I'll then finish by saying a little bit about recent results we've obtained and some of the open questions and challenges that future data is going to place. Okay, so as you're all aware, we currently have a network of ground-based gravitational wave detectors that are operating. There are two LIGO interferometers in the US. There is the Virgo interferometer in Italy and Gair in Japan. These are currently, none of them are currently online. They're all being upgraded in one way or another. And the next observing run involving the LIGO detectors will start in March of next year. So far, they've collected data in 3 separate observing runs, and over these 3 runs, we've observed slightly more than 90 events that we believe are likely to be of astrophysical origin. And these are mostly the mergers of 2 black holes in a binary, which we believe are the endpoint of stellar evolution of a binary system. But there have also been a couple of binary neutron star events and a couple of events that we think are mixed binaries that contain 1 neutron star and 1 black hole. LIGO is, as I said, about to start its next observing run, but there are also plans for detectors that will come after LIGO. One of these is going to be in space. It's called LISA, the Laser Interferometer Space Antenna. It's due to be launched in the mid-2030s, and it's an ESA-led project which has significant contributions from NASA. By going into space, you can have a much bigger detector. A much bigger detector gives you sensitivity to lower frequencies, and LISA will primarily be sensitive to gravitational waves in the millihertz band. And this means systems that are much more massive than the sorts of systems we're observing with LIGO. So the typical mass of a LISA source will be 1 million solar masses. So these are really massive black holes in the centers of galaxies that are merging following mergers between their host galaxies. There are also plans to build further generations of ground-based detectors, and there are concepts, 2 main concepts that are being developed. There's the Einstein Telescope in Europe and Cosmic Explorer in the US. There may be something called Voyager before Cosmic Explorer in the US. These are, as I said, being developed, but the hope is that they could start operation in the 2030s. Exactly when depends a lot on when funding is secured. So we have all of these detectors, and what these detectors observe is gravitational wave sources. We measure the strain of a gravitational wave source as a function of time in the detector. But what we want really to know is about the physical properties of the system. And so the way this is typically done is using Bayesian techniques. So we specify some prior distribution on the parameters of the source, and we write down a likelihood, which describes the noise properties of our instrument. And then we construct the posterior distribution of the parameters given the observed data using Bayes' theorem. So the gravitational wave specific part of this comes into specifying the likelihood. And what we typically do there is assume that the output of our detector is a linear combination of instrumental noise and some signal that depends on some unknown parameters. We assume usually that noise is stationary and Gaussian, and so we can write down a likelihood for the noise. And since the noise is just the observed data minus the signal, we can write down a likelihood for the signal parameters. And this is given in the bottom equation here. The likelihood is an exponential of the overlap of d minus h with itself. And that overlap is basically a noise-weighted inner product. And that reflects the fact that we have different variances at different frequencies in our detector noise. So at certain frequencies, we are noisier than at others. So this is the basic framework, but the trick in Bayesian inference is to efficiently draw samples from this distribution so you can summarize the posterior. And the normal approach is to use techniques like Markov chain Monte Carlo to generate a set of stochastic samples drawn from this distribution. But to do this typically needs millions of likelihood evaluations, and each likelihood evaluation requires the construction of this quantity d minus h. And so you need to be able to build a waveform h as a function of the parameters. And those waveforms, or at least the most physically complete of the waveforms that we have, are typically very expensive. And so this is a computationally intensive process because you need millions of waveform evaluations. So as an example, the very first event that LIGO observed in 2015 is this event GW150914. It was observed in September of 2015. The papers were finally published in February of 2016. And during the analysis of GW150914, a total of 50 million CPU hours were used. So this is equivalent to using 20,000 CPUs for 100 days. Now, a lot of that effort went into assessing significance. It was the first event. We wanted to be absolutely sure that there was no chance that instrumental noise could have explained it. But a significant fraction of this CPU use went into parameter estimation because we wanted to analyze the data with multiple different waveform models to check for waveform systematics and things like this. And it's also typical that in the LIGO publications to date, the catalog papers that summarize all of the events that were observed in a particular observing run appear quite a long time after the run itself is completed. So an example from O3, the O3, second half of the O3 run finished in March of 2020, but the catalogue paper didn't appear until November 2021. And a lot of that lag between collection of data and publishing results comes from the need to do lots of parameter estimation runs, and they take time using standard methods. This is only going to get worse in the future, and the reason it will get worse is because our detectors are getting more sensitive. As our detectors get more sensitive, we see more events, and so we have to do P for a larger number of events, and so we're going to need even more computational time if we keep with the current techniques. Future detectors also have wider bandwidths, so you can observe sources for longer. Observing a source for longer means that you have to compute a longer waveform, which again is more computationally expensive. There are other challenges that we'll face with third generation ground-based detectors, and especially with the laser interferometer space antenna in space. And that's the fact that sources will not be nicely separated in time. At the moment, pretty much we don't have to worry about overlaps between events in the data. We are trawling through large amounts of data to find interesting times in which there might be sources, and then we analyze those more carefully to do parameter estimation. But with LISA and to a lesser extent 3G detectors, we can expect sources to be overlapping in time and frequency. And so that's also going to pose extra challenges for parameter estimation. The other reason we might want to make parameter estimation faster is for the purposes of multi-messenger astronomy. As I mentioned at the start, a couple of the events we've seen so far are binary neutron stars. And if you have a neutron star in your system, there is matter present. And so you would expect there to be, there is a possibility then that the heating of this matter during the gravitational wave merger event might create electromagnetic emission. And this was seen for the first binary neutron star event, GW170817. So this prospect of seeing events both with gravitational waves and with EM is very appealing, and there's also science you can do with it. But you want to be able to send alerts to EM telescopes as soon as possible after you've detected the gravitational waves, and you want to be able to provide as much information as possible to increase the chances of the any EM counterpart that exists to be found. So this motivation of multi-messenger alerts has motivated the development of some methods that are currently used in LIGO. In particular, there's a method called Bayestar, which is used for rapid parameter estimation, specifically focused on getting sky locations and distances with reasonable accuracy to be used to send triggers to EM telescopes. Now, the way that these methods are made fast is by approximating the likelihood. So rather than doing full Bayesian parameter estimation, you make an approximation to the likelihood, essentially relying on the fact that most of the information about the sky location and distance come from the relative amplitudes of your source in your different detectors. And you can then get you can get very rapid triangulation of source locations in this way. So Bayestar, there are more details to Bayestar, and you can look at this paper by Leo Singer and Larry Price in 2015 if you want to learn a bit more about it. But this method gives you very quickly sky localization probability maps, which can be used then by EM telescopes to prioritize where to look for counterparts. But this method is only fast because it makes approximations. And so if you can do things completely accurately in much less time, it's going to be very desirable. And that's one of the applications we have in mind for the machine learning methods we've been working on. Another way that has been used to make the parameter inference faster is to make waveform models faster. So the real bottleneck in calculating your likelihood is calculating your waveform. And so there are a few groups that have tried to do faster parameter estimation with faster waveform models by training neural networks to learn the essentially to generate the waveform model quickly. There are a few examples of this. One I've highlighted here, which wasn't really aimed at speed. It was more aimed at including uncertainties in the waveform models. But I'm highlighting this one because I was involved with it, was to use Gaussian process regression to learn learn a waveform model using numerical relativity simulations. And yeah, the comparison here shows in the upper plot, you can see a comparison between two different existing waveform models in red and blue, and the results of this Gaussian process model, which attempts to calculate, to encode that uncertainty that you get from different waveform models, and hence fold it into parameter estimation. In the bottom, you see a comparison between a numerical relativity waveform, which we think to be the truth, and the results of this Gaussian process method, and it agrees better than either of the existing semi-analytic waveform models that we're comparing to. A third approach to make parameter estimation faster is using reduced order modeling techniques. This idea this dates back about a decade to work by a number of people, in particular Scott Field, Chad Galley, Michael Plura, Manuel Tiglio, and others. The whole framework was based on the realization that gravitational waveform spaces are much easier or much simpler than you might naively expect. So you can describe them with a much lower dimensionality than you would expect based on the length of your waveform. So what this means is that you can decompose your waveform space into a reduced basis that has fewer components, and hence, if you have fewer components, you can generate it more quickly. The extension of reduced order modeling it uses the fact that you can represent waveforms by a small number of components, takes it a step further, and you use empirical interpolation to construct your best fit waveform by requiring it to match your basis at a certain number of points. And the effect of this is that you can replace your likelihood by a reduced sum that just has a number of components equal to the number of elements in your reduced basis. And typically, this for all the waveform models for which this has been done, you can reduce the cost of the likelihood evaluation by an order of magnitude in this way. But it's a lot of work to build these reduced order models and then the reduced order quadratures from them. And it's a process that it doesn't get easier the more you do it. It's equally hard for your next waveform model because you have to essentially start from scratch. Okay, so that's the background and other techniques that are currently being used. Now I'm going to talk about the new approach that we've been working on, which is this idea of using neural posterior estimation. So the thing that is expensive about doing stochastic sampling is that you have to evaluate the likelihood at every step, and that requires you to evaluate a new waveform at every step. So the alternative is to use simulation-based inference, in which you build a neural network that generates samples from the distribution you want. Okay, now in practice, you can't generate samples exactly from the distribution you want, but you construct a neural network that generates samples from some other distribution Q of theta given D. That is a good approximation to your target distribution, which is the posterior. So the way you ensure this, you write down a neural network structure that depends on a large number of parameters and represents Q of theta given D. And then you try and optimize those parameters to make it match your target distribution as well as possible. And we do this by minimizing the average cross entropy. So this is the expectation over the posterior, which is the distribution you want to represent, of minus the log of the distribution represented by the neural network. It's relatively easy to show that this expectation over P of minus log Q reaches a minimum when P is equal to Q. And so if the absolute minimum of this loss, your Q distribution is representing P as well as it can for all choices of data. Now, because of Bayes' theorem, the expectation over the data distribution of the posterior is the same as the expectation over the prior of the likelihood distribution. And so you can exploit that in your network training, and you deduce that your loss is equivalent to the minimizing minus log Q over samples from the prior and likelihood. And so you can then construct this neural network in a simulation-based way. You sample random, you make random choices of parameters from the prior. For each choice of parameters from the prior, you generate a data set from the likelihood, and then you construct minus log Q of theta given D for that particular combination of D and theta, and you average that over all of the points in your training set. And hopefully, if you succeed in finding a good minimum, a good solution to this, you'll be getting a decent representation of your true posterior. So the advantage of this is that it's a flexible technique. It doesn't involve explicitly computing the likelihood, only drawing samples from it. And you put all of the cost of waveform generation into the construction of this training set. So in principle, you amortize that cost. So you do it once, generate your network, and then you can use the same network to analyze all of the events you observe in a given observing run. And you get quick inference in real time in return for this upfront cost of constructing the network. So the way we tried a couple of different approaches to this, which were more or less successful, and the one that proved to be the most powerful was to use normalizing flows. So a normalizing flow is a network that describes a mapping, but you use it to represent a mapping from a multivariate normal distribution, a product of standard normal distributions, to your target density. And then to draw samples from your target density, which is ultimately what we want to do, you just generate samples from these standard normal distributions, feed them through the normalizing flow, and that gives you a sample from your target density. So the target density is related to the normal distribution by this equation here. It depends on the determinant of, depends on the Jacobian of the transform. But the normalizing flow network learns both the mapping and the determinant, and so it works. For this to be powerful enough, you want the mapping to be, or for it to be easy enough to use, sorry, you want the mapping to be invertible and have a relatively simple form of Jacobian. And there are various ways you can do that. And the one that we have been using is a technique that was described in a paper by Durkin et al. In 2019. And we build the normalizing flow from a sequence of coupling transformations where those coupling transformations are represented by quadratic splines defined by a set of knots. So a coupling transformation is given by that first equation there. You set the output either equal to the input for the first half of your inputs, and then you do a transformation, you apply a transformation to the inputs to give you the outputs for the second half of your network. And the transformation we use is represented by a quadratic spline. If you do a sequence of these coupling transformations, so you have a number of layers in your network and you apply these coupling transformations at each layer, you can represent very complicated transformations between the normal distribution and hence represent very complex probability distributions, and in our case, complex posterior distributions. The normalizing flows are powerful and they work pretty well on their own, but that it's not quite enough. And so there are various other things that we do to make the network work a bit better. The first of these is to exploit the fact that we know there are reduced bases exist. So we know that waveform, you don't need all of the samples from a waveform to represent it, because you can represent any waveform as a linear combination of a much smaller number of basis elements. And so that tells you that you should be able to compress your input data in some way. So one way you could go about that is to use the fact that you have a reduced basis for a particular waveform model, and by hand do the projection onto that basis, and then train the network on the projected coefficients. But a more robust way to do it that fits more naturally with the general framework is to use a neural network to do that initial compression phase. So we start with an embedding network. We, as input, we put in all of the samples from our n different detectors for a segment of a certain length, and we typically use 8-second segments sampled at a kilohertz, it's like, well, 1024 hertz. We apply a linear projection to those inputs, and when we're training this network, we provide an initial guess, which is inspired by the notion of reduced bases. So we take the noise-free waveforms, we do a principal component analysis of them. We use the first 400 principal components as a initial guess of what projections you need to do on the input data to achieve the appropriate compression. Having done that linear projection, we then feed it into another network, which is not linear. It's a fully connected network with 48 hidden layers, and has a final output with 128 components. That second network does an additional non-linear compression of the data. And so we compress from the number of detectors times 24,000 down to 128 data points, but before applying the normalizing flow. Another refinement is to deal with the time of coalescence. So a priori, we do not know when the signal merges. We get some information about that. So from the initial trigger that prompted us to analyze the segment of data. But if you allow your time of coalescence to be unknown, as you make the uncertainty on that time of coalescence larger, you find you need more and more reduced basis elements to represent it. And so if you were trying to train a network to recover your time of coalescence directly, you would need a lot more basis elements. And so you would need a much bigger output of your embedding network in order to have all of the information you need to recover the signal afterwards. But this is a slightly frustrating situation because the time of coalescence in a detector is just a slide of the data. So it's just a shift of the whole data set. And so if you knew what the time of coalescence was, you could just shift your data so that it was aligned with time of coalescence equals 0. And then you'd avoid this problem of the increase in the basis size from having that parameter unknown. And so the problem is we don't know this a priori, and it's not an exact symmetry if you have more than one detector, because the amount you shift the data by in each detector is slightly different. It depends on the location on the sky from which the source is coming from. But we can still use this idea to improve the efficiency of the network. So this led to the idea of what we call group equivariant neural posterior estimation. So yeah, the basic idea is that we start with some guess of what the time shift we need to apply to the data is. We apply it, we recover posterior on all of the parameters of the source. That gives us a slightly better estimate of the amount we have to shift the data by. And so then we try again, shifting it by the new estimate. And then we get a new posterior distribution of all the parameters, and that gives a new estimate, and so on. And so by a process of iteration, you can converge to the true time of coalescence. So more precisely, what we do is we condition the data on not only the data, but on a blurred estimate of the time of coalescence. So we feed in an extra parameter, t hat, which is drawn from a distribution centered at the true t. And we, for training this network that has this extra input, we follow a Gibbs procedure. So we start with our guess t hat, we align the data based on that. We draw theta from the distribution q of theta given d and t hat. Then we sample t hat from this blurry kernel, so this normal distribution centered on ti, where that ti estimate comes from the sample that was drawn from the previous network, and we iterate like this. So this turned out to be much more effective than trying to train bigger networks that could learn directly the time offset you need to apply to the data. We found that with just 10 iterations of this time shifting and sampling is enough to get you to the right answer. And so this process eliminates the large uncertainty in TI, for the small uncertainty on TI, and that is enough to then use a network that has a much smaller embedding network, and hence is much more powerful. Okay, so this is then a summary of what we do, where we start with data. Oh, yeah, one thing I did not mention so far. The likelihood for the gravitational wave data depends on the noise properties of the detector. If these noise properties were fixed, then you would just train your network to by generating data consistent with those noise properties. But we find that the Pi spectral density does evolve over time, and so different events have different instrumental noise. And so if you're going to get accurate inference, you need to provide that information. And so the network takes not only the data as input, it also takes the spectral density estimated at the time of the event as input. Now, obviously, to train this network, you need to know what your distribution of spectral densities, your distribution of noise distributions is over the course of your observing run, and you typically will know this at the end of your observing run, but maybe not at the beginning. And I'll say a little bit more about that in a minute. So we provide the data and the spectral density estimate as inputs to our embedding network that compresses the data. The output of that embedding network is fed into the into the normalizing flow, and then we generate a sequence of samples from a product of normal distributions, apply the flow, and that gives us samples from the target distribution, which is hopefully close to the posterior distribution. Okay, now these networks are large, typically hundreds of millions of parameters, but as you'll see in a minute, it does appear to work well. Okay, so how do we check that things are working? So there are a couple of standard checks that we've been doing. One is to check internal consistency, and one is to check external consistency. So checking internal consistency, we use PP plots. So a PP plot, probability plot, you are computing the posterior density at which the true parameters used to generate the data lie. And so if you are generating samples from your posterior distribution, you expect the PP plot to be a diagonal line. And so what we do is we generate fake data sets in the same way we generated our training data. We apply the neural posterior estimator, we get the posterior distribution, we compute the probability at which the true parameter used to generate the input data lies, and we repeat. And if the network has trained well, the PP plot should be diagonal because it's telling us then that it is generating samples that are consistent with the data generating process. And that's what the right-hand figure shows here. These are PP plots for all of the 15 parameters that describe a gravitational wave signal. And the numbers in brackets are the p-values for the hypothesis test that there is a deviation from a diagonal line. And in most cases, these p-values are very large. There are a couple of cases where it's sort of marginally significant, but this was over 1,000 separate realizations. So it's pretty convincing. We also check external consistency. So this means that we take data that we have not generated ourselves. We've not generated in the way that is consistent with the changing data generation. And so to do that, we go to our gravitational wave detectors. We take observations of real events, and then we can analyze those real events using standard stochastic samplers, and we can analyze them using the neural posterior estimate and see whether the results are consistent or not. So the first study we did of this was using the events that are described in what is called GWTC-1. This is all of the events that LIGO and Virgo observed during the first 2 observing runs. So there are a total of 10 events. One of them was GW170817, which is a binary neutron star. The other 9 are binary black hole events. And we focused on the binary black hole events for, well, the main reason is that it is more difficult to do longer waveforms, and binary neutron stars last much longer in the data than binary black holes. I'll say a little bit more about that at the end. So to analyze these GWTC-1 binary black holes, we used 5 million waveforms for training. These were generated with a waveform model called IMR phenom PV2. The IMR phenom refers to the way in which the model is constructed. The P means it's precessing, but for those who are waveform experts, this is not a model that includes higher modes. As I mentioned before, we use these standard settings. The segments are 8 seconds long, and the range of frequencies over which we analyze is from 20 hertz to a kilohertz. And we trained for the full 15D parameter space that describes a binary black hole signal, but with the restriction that the masses of the 2 components were in the range from 10 solar masses to 80 solar masses. So this excluded one of the events from GWTC-1, which has slightly lower mass. But again, this was mostly due to the additional cost of doing longer waveforms, and extending this prior range is something that is currently being investigated. So the other aspect of training data generation is noise, and we did this by generating a bunch of stationary Gaussian noise realizations consistent with a given power spectral density, and we trained separate networks for the 2 observing runs that constitute the GWTC-1 catalog. So the first observing run, only the 2 LIGO detectors in Hanford and Livingston were online, so we had 1 detector for that run. In the second observing run, there was part of the time that only the LIGO detectors were online, and part of the time which Virgo, the French-Italian detector in Italy, came online. And so we had to have separate networks for those different cases. But this is an example of the results. This is an analysis of GW150914. GW150914 was the first binary black hole event observed, and we are comparing in the left-hand corner plot the results from our code, which we call DINGO, deep inference for gravitational wave observations. And that's shown in orange, and the blue is a comparison to stochastic sampling results obtained using the standard LAL inference code doing MCMC. And as you see, it's hard to tell on the left-hand panel, but there are two lines in each cases. In some of the parameters, you can see the differences more clearly, but the agreement is extremely good. We are clearly recovering the posterior distribution very well. The right-hand figure here shows the sky location, again in orange and blue, comparing the two sets of results, and we see again the agreement is very good. But whereas the LAL inference results took days to produce, the DINGO results took about 20 seconds to generate 50,000 samples. So we have achieved the goal of having robust parameter estimation in much less time. So that's one event, but we can do a more systematic comparison over all events by calculating JS divergences. There are various metrics you can use to compare probability distributions. We used the JS divergence, but we could have used other metrics like KL divergence or other things. And this table summarizes the JS divergence in units of nats. And the rule of thumb is that two distributions are indistinguishable if the JS divergence is less than 2. We see in this table here, for the vast majority of events and the vast majority of parameters, the numbers are below 2. There are a few cases where the numbers are a bit bigger, but these were mostly events that were close to the edge of the priors, and these numbers came down. We trained networks that use slightly wider initial prior ranges. Okay, so was the status of about 6 months ago. Over the last 6 months, we've been working on various refinements. One of these is was partly motivated as a way to convince people that the results were robust, partly as a way to add robustness if the network is not quite trained enough. But the idea is that we can add an extra stage. So we first generate our posterior samples using DINGO. We then apply an importance sampling step. So importance sampling is probably familiar to many of you. It's a widely used technique in Bayesian sampling. If you want to generate samples from a particular distribution, you generate samples from another distribution and then re-weight them. You assign weights that are basically the ratio of the distribution you want to be sampling from to the distribution you are sampling from. And you can then do inference over your target distribution by doing weighted sums of samples drawn from the sampling distribution. So you can use neural posterior estimation to generate samples to do importance sampling. It's a good way to do this because of the way in which the loss function is minimized. You expect the distribution to be broader than the target distribution. So it should have probability mass everywhere where your target distribution has probability mass, which is an important requirement of any good importance sampling algorithm. The figure on this slide shows a comparison of the log probability computed from the neural density estimate on the horizontal axis and the log probability computed directly by evaluating the product of likelihood and prior for the source of interest. And you see that the NDE is doing a pretty good job. The samples are pretty well along the diagonal. At low values of the target probability density, we're tending to overestimate the probability with the neural density, and that's consistent with this idea that the MPE tends to have a broader distribution. but these samples are very low weight in the final distribution. And so this fact that a plot looks like this suggests that the neural density estimate is working well. Now you can quantify this a bit better by computing the effective sample size. You calculate the sum of the weights squared divided by the sum of the squares of the weights. If this number is close to the number of samples you started with, then your reweighted samples are all independent, and it's basically telling you that there is a very little difference between the sampling distribution and the target distribution. If this effective sample size is small, it means that there's big correlations in the samples. There are some weights that are very big, and that's telling you that your sampling distribution is not a good representation of the target distribution. And so by doing this important sampling step, applying it to your neural posterior estimation samples, it gives you a direct way to assess whether the samples are any good or not. If you get an effective sample size that is close to the number of samples, then you know that your network has done a good job. If it is much smaller, then it hasn't and maybe needs some more training. So it's another diagnostic that you can use of the efficiency of the network. And if the effective sample size is not too small, you can always then use these weights and by generating more samples from your neural posterior estimator, you can get a decent number of samples from the target distribution using this reweighting procedure. So here's an example of this. It's a comparison for GW15 and 914 using a phenom model. The left-hand side, we're comparing LAL inference results, so MCMC results, to the results of DINGO. And then the right-hand side, we see what happens after you apply this importance sampling reweighting step to the DINGO samples. You see, whereas in the left-hand panel, it looks okay, but not great. As soon as you apply this important sampling step, you recover the target distribution almost perfectly. And in this case, the effective sample size was 28,000, which was 14% of the number of DINGO samples that were initially generated. So this important sampling step is a way to build additional robustness into the procedure as well as a diagnostic of the network. Obviously, it comes at a cost, and that cost is you now have to evaluate the actual likelihood for all of the samples that are coming out of your network, because otherwise you cannot compute the importance weights. And so that means the whole procedure is somewhat slower than it would otherwise be. But it does add robustness. And so we think potentially this is a wise thing to be doing. Another recent development is considering noise variability. So I said that we need to feed in the PSD estimated at the time of the event, but obviously you need to train your network on some set of PSDs that you think are representative, and LIGO noise tends to vary between different observing runs and over the course of a run. But you really want to have your neural posterior estimator ready to analyze events right from the start. And so you need to somehow train your network without actually knowing what the noise is going to be. So we've been working on this and in particular comparing 3 different approaches to it. One is to just use the noise early in the observing run as a proxy for the noise throughout the run. You train the network using PSDs measured in that first week or so of the observing run, and then hope that it's representative of the rest of the run. We have also tried a new approach in which we essentially use the way in which the noise varied through a run in early observing runs to infer the distribution that the noise might have over a future run. And so we use a combination of that distribution with noise measured early in the observing run to simulate the noise distribution for training. And then there's a third case, which is a perfect knowledge case, we call oracle. And that's when you use the noise measured over the full observing run to train the network. So this would mean you wait until the end of the run before you analyze any of your events, which is not the use case we had in mind, but it's at least a reference point to compare the other two approaches to. So this is what happens. The left-hand panel is an example corner plot comparing these different approaches. The blue curve is DINGO with importance sampling. So that's doing a final correction to the PSD measure the time of event. So you actually reweight to the exact likelihood. The other dashed curves show the results before you did any important sampling reweighting based on training either on the early observing run noise in green or the synthetic noise in red or this oracle noise that uses the whole distribution which you don't know in advance in orange. And we see there's a relatively, for some parameters, jet mass and luminosity distance, there's very little difference, but for sky location, which is something you really care about for sending EM alerts, the synthetic noise actually gets very close to oracle and is also very close to the reweighted result, which is the correct answer. And they're both much better than using the early observing run noise. And so we think that generating noise data for training in this synthetic approach should be good enough for future detectors. Okay, so final couple of elements of recent progress. We've started to train on more physically complete waveforms. The early results I showed were just using waveforms that just include precession. But the most physically complete models we have now that are for circular orbits at least include precession and higher modes, and we've generated networks that work for both of the models that are currently being used. Phenom XPHM and SEOB and RV4 PHM, and so things seem to be working well in that case as well. So I've been really out of time, but I wanted to finish by highlighting a few challenges that we haven't fully solved yet, but we need to think about, or somebody needs to think about in the future. So one of the challenges is population inference. We care about parameters of individual events, but it's more important when we combine those parameter measurements from individual events to say something about the wider population. This is typically done using Bayesian hierarchical modeling. Now, the use of neural posterior estimation or other techniques to generate fast posterior samples could be very useful for Bayesian hierarchical modeling because these typically rely on reweighting samples from the original events and having the ability to generate lots of samples from those original events quickly will make population inference faster. But as you combine events, you're going to be more sensitive to features that are in the tails of your distributions, which you may or may not be resolving well. And so this application to hierarchical modeling may place extra constraints on the, or extra conditions on the precision of the neural posterior estimator that you need to ensure are satisfied. You can also, so we've just started to look at this population inference from a purely machine learning perspective, because it's natural to ask whether you can learn the full population posterior distribution directly. And we have preliminary results that look at that, that suggest that might be possible. There are various different approaches you can take to this. One we're currently exploring is training the population posterior network using sets of samples from individual events that have been generated with DINGO. And that approach includes some kind of error correction to the original samples and seems to be working relatively well, though this is in the early stages of development. Other challenges that we're going to have to face in the future, I've mentioned this a couple of times, that binary neutron stars we haven't done yet because their waveforms are longer, and that makes the size of reduced bases bigger. So you need a bigger output from your embedding network, and that means that your normalizing flow network will also probably have to be bigger and hence harder to train. This is only going to get worse for future detectors, where the bandwidth will be wider and you'll be observing sources for days for ground-based detectors and years for space-based detectors. So we need to develop techniques to deal with that. One is to have better embedding networks that can still compress things a lot. Another approach we've been playing around with is whether we can adapt this group equivariant neural posterior estimation approach to apply to intrinsic parameters as well. But again, we haven't got very far with that, but it's something that needs to be dealt with. Another challenge for future detectors is non-stationary noise. Most of the events we've observed so far have not been adversely impacted by instrumental artifacts, but for longer signals, that's not going to be the case. All of LISA's signals will overlap glitches and gaps because they last essentially most of the duration of the data set. And already in LIGO, the first binary neutron star event, GW70817, was in data with a big glitch. And so accounting for these noise non-stationarities and dealing with them is important. But it's something that can naturally be done in a neural posterior estimation framework, because all you need to be able to do in order to deal with non-stationarities is generate data sets that include them. So as part of that training data generation, you can include noise artifacts and hopefully therefore handle them in the data as well. And then the final issue is dealing with data that contains more than one source that's overlapping. We haven't thought about this much at all yet, but it will be a big problem for LISA in particular. All of the sources will be overlapping with other sources. And so if you want to use these kinds of techniques, you need to your network to be able to simultaneously infer parameters on multiple sources at the same time, or do something iterative, perhaps, that sequentially identifies the loudest source in the data. But that is an open problem, which hopefully we will solve by the mid-2030s when we have data from LISA. Okay, so that is the end. Leave the summary here, but the key takeaway is that we've been working on techniques for generating posterior samples that are accurate samples from the true Bayesian posterior distribution in a fraction of the time that standard methods take. We have results that look very good using this neural posterior estimation approach based on normalizing flows. So far we haven't, as we've made the problem that we're trying to solve more complex, the techniques have continued to work. Whether that will continue to overlapping sources, longer data sets, and so on, I don't know. But everything looks very promising so far. And so it seems to be a very good approach that's working well for us and could well be useful in other fields as well. Okay, thank you.
Okay. Big thank you, Jonathan, for this. Okay, so we're running a little past time, but maybe we can stay on for a question or two. Does anyone have any questions? Phil, you want to go ahead?
Sure. Yeah. First of all, yeah, thanks for this talk. This is fantastic. It's really interesting. I was wondering what seems like the model is very, very large. Like, and I kind of calculated off the top of my head that the size of the model is like almost the same size as the data set you're training on. I was wondering if there'd been like some exploration terms of like compressing the model, right? And there are a lot of ways to compress it, right? So I was wondering, what strategies you had looked at, or if you had looked at strategies and other things, other ways.
Right. So I mean, the short answer is no. We haven't done extensive explorations of the most efficient way to be doing this. We made the network as complicated as it needed to be for it to start working, and were at that point content, which is perhaps not a good strategy, but yeah, I mean, I think you're right that we should probably be able to do what we are doing with simpler, well, with smaller numbers of parameters, but we haven't done extensive explorations of that so far.
Okay, thanks. Yeah. Well, that's good to know. There's lots of room for exploration. Okay, thanks.
Any other questions? Okay, so as I said before, I think at least within the MMA group, we're super excited to be trying out some of this stuff and getting to use it. So huge thank you to Jonathan for coming and giving the talk today. But if no other questions, then I think we'll close, and yeah, have a wonderful Monday, everyone.